So the last expression that we found in the previous slide, on the left-hand side, we have a bare 1 pi vertex, and that diverges in the epsilon going to 0 limit. It is divergent. On the other hand, this renormalized 1 pi vertex is finite as epsilon goes to 0. This factor is finite. Moreover, this has both implicit and explicit mu dependence, as I have pointed out earlier. Okay. Now, in a renormalized, in general, a renormalized observable will be written in terms of all sorts of 1 pi vertices. Say O tilde n. This is, we haven't discussed exactly what kind of observables, like in a scattering theory, one should consider. But I think in QFT1, you have learned how to write the scattering matrix elements in terms of correlation functions, and those are the Green's functions. And so I haven't discussed that, but I'm assuming that you are familiar with that. Those are the physical quantities you calculate, and they will depend on the external momenta, the coupling lambda, which has implicit mu dependence, m, which also has mu dependence, and then there is an explicit mu dependence of O tilde n, and this will be written written in terms of all sorts of the 1 pi vertices, gamma tilde 2, gamma tilde 4, and so on. And this gamma tilde 2 has this structure p square plus m square minus omega square of p square. And we have done the calculations of this. This omega square will have divergence, and you add counter term and renormalize it. So that omega square is finite. And all these higher order vertices, gamma tilde 6, gamma tilde 8, and so on, they have divergences only when this 2-point and 4-point vertices appear as subgraphs. And these divergences will be cured when we use the renormalized versions of gamma tilde 2 and gamma tilde 4. So these are cured when renormalized gamma tilde 2 and gamma tilde 4 are used. And the general dependence of gamma tilde 2 and gamma tilde 4 is on a set of quantities, lambda of mu, m of mu, there is an explicit dependence on mu, and these are let us go back to this the original calculations, where we see that finite terms coming out from the calculations of the loop diagram. So for example, in here we calculated the one loop diagram contribution to the 2-point function, the finite part of it, which is given by half psi 2 minus log m hat square. And then we introduce a counter term here, which is capital F1, and then at order lambda square, we have several diagrams, and in the 4-point function, we have a finite contribution coming from G1, which is also at the one loop level. We have calculated this expression, which is given by this. And at this level, there's a new counter term, which is where the finite piece is capital G1. So this small G1 is a finite piece calculated in the original Feynman diagram, and capital G1 is a finite ambiguity. So small G1 is known. Similarly, small f1 is also known. It's a specific function. Small f1 is known, is a specific function, but capital F1 is an ambiguity, is a finite ambiguity in the counter term. So so the pattern that we see here is that after adding the counter terms, we not only have the mu and lambda dependence, but also we have the known finite portions coming from the original Feynman diagrams, and unknown or ambiguous finite portions coming from the counter term diagrams. So these collectively, the known finite portion coming from the Feynman diagrams, original Feynman diagrams, can be written as this way, and this is a set of all such functions. So it is like the f1, g1, f2, and so on. And there is a set of infinite number of unknown finite ambiguity coming from the counter terms, and this is the set of, so let me write it here, set of f1, g1, h2, and so on. Okay, so this mu is completely arbitrary. This is finite known finite pieces from original Feynman diagrams, and this one is finite ambiguities. at epsilon equals 0. Okay, in the epsilon going to 0 limit, this gamma tilde 2 and gamma tilde 4 will be finite, but then they will be dependent on this bunch of factors. Okay, now out of these, we don't know how to interpret mu and how to interpret these finite ambiguities. So the question is, how to deal with mu and these finite ambiguities. The answer to this mu question is that it can be identified with the overall energy scale. And this one can be fixed by relating renormalized couplings m mu and lambda mu to proper vertices gamma tilde 2 and gamma tilde 4 at a particular scale. And so basically this, I mean, you can, we shall see two scenarios, at least two scenarios of how we can fix them. But basically fixing this is in some sense equivalent to defining the renormalized coupling at a particular scale. So how do we identify mu as an overall scale that observable, endpoint observable, renormalized endpoint observable, which depends on the external momenta, and then lambda mu, m mu, and mu can be written as e to the power d times O tilde in, say, scaled x comma lambda mu m mu over e and mu over e, where x is the set of ratios of external momenta and the and say e. Where E is an overall scale, overall energy scale. Depending on P1 to Pn, and D is the mass dimension of the quantity. So if d is the mass dimension of the quantity, then you can always write it as e to the power d, e as identified as an overall energy scale of the process, and then O tilde ns will be something that is dimensionless, and therefore there the arguments that are appearing in that for that function are also dimensionless. So these are x is a set of all these ratios of momentum versus the overall energy scale, and then also for the mass parameters will be replaced by the ratios of the mass parameters and this overall scale. And then once you identify the overall scale at which the observable is being defined, then you can choose mu to be same as that scale. So that is how mu is physically interpreted, because E is identified physically. It is a scale, energy scale. For example, if you are scattering, if you're looking at a scattering experiment, then the scattering cross section will have an energy scale involved, and the energy scale at which say for example the center of momentum energy of the process. This is the energy scale at which the experiment is being done. And once you identify that, you can scale that energy scale out of the quantity. And from dimensional analysis, you know that it should be e to the power d, which means that the O tilde ns is basically O tilde n divided by e to the power d. Since O tilde n scales like e to the power d, O tilde n divided by e to the power d is dimensionless, and it should be possible to write this quantity in terms of those dimensionless parameters. Once one does that, E now is a physical scale, then mu is can be interpreted physically by equating with that scale. So once you choose mu equals E, then the same result will be given by e to the power d times O tilde ns x lambda as a function of E, m as a function of E by E, and 1. Next, define the renormalized parameters, the couplings, m mu and lambda mu, such that here is one scenario, and the scenario is that you define lambda tilde to the 2-point vertex as the as given by p square plus the coupling at p square is equal to 0, and lambda tilde 4, the 4-point vertex, as minus lambda mu at pi equals 0. So basically what we are using, the idea of the idea behind using such a definition is that m lambda are the couplings, and these couplings means they define the potential of this. So the effective potential is the part of the effective action which is at p equals 0. So if you take the effective action and take the constant field configuration, then the effective action reduces the integral of the effective potential, and this effective potential has the renormalized effective potential defines the renormalized couplings. It is that idea. So in terms of momentum space quantities, you are basically defining a gamma tilde 2 as gamma tilde 2 to be the effective coupling at p square equal to 0. Similarly, you take gamma tilde 4. In gamma tilde 2 and gamma tilde 4 both have general expression for non-zero values of p. You set p equal to 0 and identify the effective couplings, I mean the renormalized coupling from them. So that is the idea. And then if you recall the expressions for gamma tilde 2 and 4, which is, say, gamma tilde 2 will be given by this expression. So gamma tilde, recall. So there is a tree-level diagram which is given by p square plus m square. Then the loop diagram is given by m square times lambda hat times half psi 2 minus log m hat square. Now, this is the 1 pi vertex, but when you calculate gamma tilde 2, it is given by negative of the, this is, if you recall the discussion of this is being omega square, and the gamma tilde square is p square plus m square minus omega square. So negative of that. So, so minus so epsilon, 1 over epsilon is the pole term that will be cancelled by the counter term. So what we would have is that m square lambda hat minus m square lambda hat times this. So I have already written m square, so minus lambda hat and then the counter term contribution, which is minus m square lambda hat f1, capital F1. So m square lambda hat has been written. I have written an extra factor of half outside, so minus 2 f1. Similarly, gamma tilde 4 will be given by the expression, let's see where it is. In the epsilon going to 0 limit, we have minus lambda, and then 3 lambda times lambda hat, epsilon going to 0 limit, mu to the power epsilon goes away. This pole will be cancelled by the counter term, and plus g1. So let us write that much. So minus lambda times 1 minus 3 lambda hat times g1 and minus capital G1, which is the counter term. Plus order lambda cube. Now we have to calculate this at pi equals 0. So let us see what this is. 1 minus 3 lambda hat. Then small g1. Small g1 is given by this, which is half psi 1 minus 2 g1. And we should calculate it at pi equals 0. Now, when I set pi equal to 0, then this A has to be calculated. A calculated at that value of the external momenta. If we look at A, let's see where A is written. Maybe it's in results. Yeah. This is the expression for A. And if you set all the pi's to 0, so we shall use this expression and show that this goes in the p going to all pi is going to 0 limit. It approaches 6. That we shall show later. Let me just do the calculation here. So the claim is that this goes to 6, and therefore 6 by 3 is 2, and that minus 2 cancels this plus 2, and we have psi 1 minus log m hat square minus 2g1. And in this expression, in the gamma tilde 2 expression, if you set p square equal to 0, then we have m mu square times 1 minus lambda hat over 2 psi 2 minus log m hat square minus 2 f1 plus order lambda square. So you could write it as minus lambda plus 3 by 2 lambda hat psi 1 minus log m hat square minus 2g1. Now the criteria that we are using here, which is that gamma tilde 2 should be m square at p square equal to 0. And gamma tilde 4 should be minus lambda at p equal to 0, pi equal to 0. So the first condition, when gamma tilde 2 should be m square at p square equal to 0, tells us that gamma tilde 2 should be, so this is what when we calculate p square. So then it should be m square. That means we should pick only one and the rest should be 0. And that allows you to fix f1 in terms of, so this psi2 minus log m hat square minus 2f1 should be 0. So this says f1 should be equal to half psi2 minus log m hat square. And from the gamma tilde 4, it should be minus lambda, and therefore this term must be 0, and that shows that G1 should be equal to half psi1 minus log m hat square. Similarly, if you do calculations at higher order, like order lambda square, or in this case at order lambda cube, then at each order the coefficients must vanish, and at each order new finite ambiguity appears, and they are solved by those equations, because you will maintain this relation that gamma tilde 2 at p square equal to 0 is this. So all the higher order terms must vanish, and each coefficient of a specific power of lambda should be set to 0, and that will allow you to find all these finite ambiguities in terms of known quantities. So once you find the finite ambiguities in terms of known functions using this particular prescription, then one can substitute them back into the original expressions for non-zero values of p square in both gamma tilde t and gamma tilde 4. So actually, I should also write here calculated at pi equals 0. So once you substitute that, then these expressions, and then you turn on the non-zero values of the momenta, and that will give you definite expressions of gamma tilde 2 and gamma tilde 4 in terms of in terms of p and p's and the renormalized couplings lambda and m, and there is no ambiguity in that in those equations. The ambiguities are lifted. For example, in here, in the case of this coefficient here up to this order that we have calculated, there is no p dependence, and therefore this this value of f1 entirely cancels our lambda terms. But if you look at the gamma tilde 4 result, then we had to take the pi going to 0 limit of this function, but this function is a non-trivial function of the momenta of the 4 momenta that are involved in the external leg of gamma tilde 4. So once we find G1 in terms of these functions, so when you substitute it back, this term will cancel psi1 and minus log m hat square, but and with there'll be a so it will be, the expression will be left with 2 minus 1/3 a, where these are non-zero values of p, and that's a non-trivial result for gamma tilde 4, which depends on some of the terms at each order in lambda will get cancelled because of these choices. But if any term at any higher order in lambda is independent of momentum, then that term will disappear according to this prescription completely, because setting p equal to 0 does not change that term, and you are setting that term to 0. But if any term at higher order in lambda, at any order in lambda, both in gamma tilde and gamma tilde 2 and gamma tilde 4, if that is p dependent, you see that we have observed that the earlier that though the residues of the poles have polynomial dependence, and those are homogeneous polynomials in P and M, but that is not true for the finite parts, and those finite parts of the Feynman diagram calculations appear here in these terms, and therefore there can be non-trivial P dependence involved. If non-trivial P dependence is involved there in a particular order of lambda, then those terms will survive after you substitute the finite ambiguities that you found in this way. And therefore, at a non-zero values of P square, both gamma tilde 2 and gamma tilde 4 will be non-trivial functions. But there are no finite ambiguity, and they are written in terms of the renormalized couplings. Now, if you go back to this to an observable scattering theory, which as I have mentioned, that these are written in terms of various endpoint 1pi vertices, which and all of those calculations are finite except for gamma tilde 2 and gamma tilde 4 subgraphs, and that's how you write the entire result, since gamma tilde 2 and gamma tilde 4 are now written in terms of renormalized couplings. When you substitute them back in here, this quantity, this observable, is written in terms of the renormalized couplings. Basically, this expression, both lambda e and m e. Mu is set to be e, as I have chosen. You can choose mu to be e, as I have mentioned before. And then that means this expression, when you have this expression as a power series in lambda, then at a particular order in lambda, you can truncate the expression because you are always calculating things approximately, and then you can do experiments and get the results, observational result, and from there you find the values of you do a finite number of experiments and find this only two parameters, values of the two parameters that are involved. And once you measure the values of those two parameters, you can predict infinite number of other observables using those values that we have calculated using the finite number of observations. You can predict in infinite number of other results at the same energy scale, because you have calculated m and lambda at a particular energy scale. How we can change the energy scale is something that I will discuss later. But this is what this is how this is just a demonstration or some explanation of how this program of renormalization is supposed to be used in explaining observational results. And this whatever I just described in number 2, which is this one, is actually called renormalization prescription. So the particular way of defining these renormalized quantities by elevating the finite ambiguities of the counter term is called a renormalization prescription. So let me write it down here. And this renormalization prescription is not unique. It depends on the applications, the calculations that one is trying to do. Some prescription may be more useful, more convenient to use than others, and I will explain that. I will consider another renormalization prescription in the next slide, and I shall discuss that.